Imagine you could fly in a straight line forever, past the planets, past the galaxies, past every last faint smudge of light in the sky. At some point your brain wants to ask a very simple question. What happens when you reach the end? Do you slam into a cosmic wall? Do you pop out on the other side like a video game? Or does space itself just keep going, without ever giving you the satisfaction of an edge? Any answer you choose has something deeply weird hidden inside it. So if you enjoy chasing that weirdness to see where it leads, remember to like this video and subscribe, and let us go to the edge of what we can think. Everything you have ever touched comes with a built-in boundary. A room ends at its walls, a road ends at a cliff, or a sign that says dead end. Your coffee mug stops where the ceramic meets the air. Your own body is outlined by skin that tells you where you finish and the rest of the world begins. From childhood onward, we learn that to understand something, we first find its edges and ask what lies just beyond them. So when humans first stared at the night sky, it was almost inevitable that they asked the same question upward. Where does that end? The stars look like they are painted on a curved surface overhead. The sun and moon rise from one side of the world, glide across that dome, and sink behind the opposite horizon. The simplest story is that the heavens themselves are a container, with stars as decorations and some kind of lid over our heads. Ancient peoples did not have telescopes or spectrometers or space probes. What they had was story, geometry you can do with your eyes, and a deep need for a world that feels contained. The Babylonians, living 3,000 years ago, imagined Earth as a flat disk floating in a vast cosmic ocean. Above this ocean stretched a solid dome that held back the waters of chaos. The stars were little holes in that dome, pinpricks where divine light leaked through from outside. It was a compact, well-behaved universe. Below lay the underworld. Above lay the dome. Beyond that, the realm of the gods. Everything had its place, and the edges between realms were crisp and meaningful. This was not just superstition layered over ignorance. It was a careful attempt to explain a sky that really does look like a hard shell surrounding a small human world. Elsewhere, people wrapped the same sky in different imagery. Along the Nile, some Egyptians pictured the sky as the goddess Nut, her body stretching from horizon to horizon as she arched over the earth. The stars were jewels on her skin. In ancient Indian stories, the solid ground rested on elephants which stood on a turtle, which itself stood on some deeper cosmic creature. Sometimes a serpent coiled in the dark. The details change from culture to culture, but the pattern is the same. The universe is finite. It has layers. It has a top and bottom, a sense of inside and outside. Your world is literally held up by something. Confusion about the infinite is replaced with comfortingly solid edges. Then the Greeks did something subtle and dangerous. They brought geometry into the heavens. Around the time of Aristotle, about the 4th century before the Common Era, thinkers built a new model. Earth sat motionless at the centre. Around it nested transparent spheres, each one carrying a celestial object. The moon rode the innermost sphere, then Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally a great outer sphere carrying all the fixed stars. These spheres rotated in perfect circles because circles were thought to be the most perfect possible motion. For nearly 2,000 years, this Aristotelian cosmos defined reality for the Western world. It was clever. It explained why stars seem fixed relative to each other while planets wander. It gave every object a natural place and natural motion. Heavy stuff moved inward toward the centre, light stuff upward toward the heavens, and the perfect circular motion of celestial spheres set them apart from the messy straight-line motions below. Most important for our question, this was a universe with a sharp edge. Beyond the sphere of fixed stars, Aristotle said, there was nothing at all. Not thin air, not empty space, but a total absence of distance, direction, or possibility. The concept of beyond simply did not apply. At first, that feels satisfying. The universe ends at a crystal shell. Outside it, there is not even a place where something could be. The story ties off neatly. Yet even in the ancient world, that neatness started to itch. A philosopher named Archytas posed a question that sounds disarmingly like a child poking holes in a bedtime story. Imagine you travel somehow to the outermost sphere of the stars, right up against the supposed edge of the universe. Now picture yourself holding a spear and thrusting it outward. What happens next? If something stops the spear, then that something must exist, which means it is part of the universe after all, so the edge you thought you reached was not the true edge. The universe is at least that little bit bigger. If nothing stops the sphere, if it flies forward unhindered, then space must continue beyond the sphere. In that case, the universe does not end where Aristotle said it does. Once again, the edge has slipped away from you. Either way, you do not find a clean final boundary. You just discover that your earlier picture of the edge was wrong. This little spear thought experiment cuts much deeper than it seems. It reveals that our minds are trying to treat space itself as if it were an object inside something larger. A table has an edge because it is sitting in a room. A country has a border because it sits on a planet. Even a bubble has a surface because it floats in air. But space is the arena that contains objects. It is the stage on which the props sit and the actors move. Asking where the stage ends in the same way you ask where a prop ends is already sneaking in a contradiction. You're trying to imagine space inside a bigger space and call that bigger thing the real stage. So when we ask where the universe ends, we are really asking two questions at once. One of them is physical. How far can we see? How much stuff is out there? Does space loop back on itself? The other question is deeper and more slippery. Are we even using the right kind of intuition? Or are we like fish asking where the water stops without knowing what it means to be outside water? For most of human history, the urge for clean edges won. We wanted domes, shells, turtles, anything that would make the world feel contained. The story of modern cosmology will gradually pry those edges away and replace them with something stranger. Not a wall you could ever crash into, but horizons, curvatures, and limits of knowledge that force us to rethink what an edge even is. For nearly 2,000 years after Aristotle, the crystal sphere universe felt solid. Philosophers refined it, theologians wrapped it in meaning, and everyday experience seemed to confirm it. The sky still arched overhead like a dome, the stars still behaved like lights pinned to a surface. Nothing in daily life suggested that space might be anything other than a finite shell wrapped around a small, important Earth. The edge question seemed answered. Outer sphere, then nothing. Story complete. Then a piece of glass broke it. In the early 1600s, Galileo Galilei pointed one of the first telescopes at the sky, and the supposedly perfect heavens immediately started misbehaving. The moon was not a smooth, polished sphere. Through his small instrument, its surface showed mountain, valleys, and impact scars, more like a bruised stone than a divine lamp. The sun, which was supposed to be flawless and unchanging, carried dark spots that appeared, drifted, and faded, proving the sky itself could change. Most damaging of all for the old picture, Galileo found 4 tiny points of light near Jupiter that changed position night after night. Watching patiently, he realized they were moons orbiting Jupiter. Not Earth, not the Sun, a miniature solar system tucked inside the larger one. The message was brutal. The rule that everything must orbit Earth was not a rule of nature, it was a human assumption. If Jupiter could have its own little system, why should our planet be the cosmic center at all? These discoveries chipped away at more than religious pride. They attacked the idea that the heavens were built of a special kind of matter, moving in a special kind of space. If the moon had mountains, it was rocky. If the sun had spots, it changed. If Jupiter had moons, circular motion around Earth was not universal. The sky and the ground began to look less like separate realms and more like 2 parts of one continuous world. By the late 1600s, Isaac Newton pushed that idea to its logical extreme. He turned the universe from a nested set of shells into an infinite stage. In Newton's view, space was absolute, rigid, and the same everywhere. Time marched forward at a steady rate, also the same everywhere. Inside this unchanging framework, every object pulled on every other object through gravity, with a force that grew stronger for heavier masses and weaker with distance. Suddenly there was no need for invisible crystal spheres. The moon orbits Earth because Earth pulls on it. Earth and the other planets orbit the Sun because the Sun pulls on them. Jupiter can have its own moons for the same reason. You do not need special heavenly matter, only the same laws everywhere. The calculus Newton developed let him write down equations that described both falling apples and orbiting planets with the same simple rules. It was a staggering unification. But look at what that unification did to our sense of the edge. In Newton's picture, space does not stop. Nothing in his equation says there must be a boundary where coordinates end. the simplest assumption becomes that space extends forever in all directions. No center, no outer shell, just an infinite uniform stage dotted with stars and clouds of gas. The comforting container universe dissolves into something that has no obvious outside at all. That sounds grand at first. The mind likes infinite vistas in poetry and philosophy, yet the physics of an infinite universe comes with nasty headaches. If matter is sprinkled more or less evenly through endless space, then every region of space feels the pull of matter in every direction. Why does it not all clump into one gigantic pile? If the universe has no center, what stops gravity from choosing one anyway and dragging everything into it? Newton saw this problem very clearly. In fact, he worried about the stability of an infinite universe. One of his responses was to imagine matter arranged in a perfectly balanced way in all directions. In such a configuration, he argued, every pull would be balanced by another pull, so nothing would collapse. But this balance is like trying to stand a pencil on its tip. Any tiny disturbance would make the whole arrangement fall one way or another. He also hinted, somewhat uneasily, that perhaps the creator occasionally nudged things back into balance, preventing a full-scale gravitational collapse. That might satisfy a theologian, but for physicists it felt like a patch. You could swap in any miracle you like to fix any calculation. The deeper point remained. Infinity plus gravity is not as simple as it looks. The old tidy edge had been removed, but the replacement was not a peaceful, eternal star field. It was a system that raised frightening questions about whether it could even exist without tearing itself apart. Over the next 2 centuries, these questions grew sharper. As telescopes improved, astronomers saw more and more stars, more hazy blobs, more hints that the universe might be far larger than the Milky Way alone. Yet the basic Newtonian stage remained the backdrop. Space was still absolute and probably infinite. Time still ticked. Gravitation still linked everything to everything else. The real unknown was no longer what lay beyond the outer sphere. It was how far the stage extended and whether an infinite stage with gravity could ever be stable. The edge question had quietly shifted. Instead of asking what the universe might be sitting inside, thinkers now asked what kind of thing space itself was. Was it a substance, a backdrop, a relationship between objects? Could it curve or flex, or was it a rigid container? If it was infinite, did that infinity have any meaningful physical consequences, or was it just a mathematical convenience? Newton had answered the old dome and turtle stories with cold, precise rules. In doing so, he removed the obvious walls and replaced them with something more unsettling. A universe that might have no spatial edge at all, but whose very infinity raised new paradoxes. To go further, humanity needed not just better mathematics, but better measurements. We had to stop guessing how big the universe might be and start actually measuring the distances to the lights in the sky. Only then could we see whether the infinite stage was a poetic flourish or a description forced on us by data. It is one thing to say the universe might be infinite in some abstract way, and another thing entirely to measure how far away a real star is. The sky is a flat pattern to your eyes. Bright dots on a dark dome. Nothing in that image tells you which star is near and which one is unimaginably distant. Before we can talk about edges, or the lack of them, we have to answer a more basic question. How do you turn that 2-dimensional picture into a 3-dimensional map? How do you put rulers on the sky? The first rung of that cosmic ladder is something so simple you can test it with your own hand. Hold out a finger at arm's length. Look at it with your left eye, then with your right eye. Your finger seems to jump back and forth against the background. That apparent shift is called parallax. It happens because each eye sees your finger from a slightly different angle. The closer your finger is, the larger the shift. The farther it is, the smaller the shift, until at some distance it becomes effectively invisible. Stars do the same trick, only with Earth's orbit playing the role of your eyeballs. As our planet moves around the Sun, our viewpoint shifts by about 300 million kilometers over 6 months. Nearby stars appear to slide very slightly against the backdrop of much more distant stars. Measure that tiny angle and you can use basic geometry to get the distance. In principle, this is simple school-level trigonometry. In practice, the angles are absurdly small, even the nearest stars shifted by less than 1 arcsecond. An arcsecond is 1 part in 3,600 of a degree. Imagine dividing that tiny wedge of a circle into 3,600 thinner slices and then trying to measure one of them. That is the precision astronomers needed from crude 19th century instruments. It took until the 1830s for Friedrich Bessel to pull it off. He measured a parallax of about 0.3 arcseconds for a star called 61 Cygni, and found it lay roughly 11 light years away. The number itself was shocking. 11 years for light to reach us from a single star. Parallax gave us the first solid rung on the ladder. Not guesses, not philosophical arguments, but real distances to real stars. Yet this method has a hard limit. As you look farther out, the parallax angles shrink until they are drowned in measurement noise. Even with modern technology, parallax alone can only reach a few thousand light years before the tiny shifts vanish into uncertainty. That is a big neighbourhood by human standards, but a small patch of the galaxy. To climb higher, we needed a way to pick out cosmic light bulbs whose true brightness we could know in advance. Then we could compare how bright they look from Earth to how bright we know they are, and use that to calculate distance. These are called standard candles. The next major rung on the ladder came from someone who was not allowed to operate the telescopes she revolutionized. In the early 1900s, Henrietta Swan Leavitt worked at Harvard College Observatory, studying photographs of a nearby dwarf galaxy called the Small Magellanic Cloud. She focused on special stars called Cepheid variables that brighten and dim in a steady repeating rhythm. By carefully measuring their periods, she noticed a pattern. The longer a Cepheid cycle, the brighter it really is. A star that takes 10 days to pulse is intrinsically more luminous than one that takes 5. Here is the crucial insight. All of the Cepheids in that dwarf galaxy are roughly the same distance from us, so the differences in how bright they look on the sky must come from differences in how bright they really are. Plot their periods against their apparent brightness and a clean curve appears. That curve is a cosmic cheat sheet. Once calibrated, it lets you take any Cepheid anywhere in the universe, measure how fast it pulses, and read off its true power output. Compare that to how faint it appears, and you get its distance. Henrietta Leavitt's relation turned Cepheids into the first powerful standard candles. A few decades later, Edwin Hubble used that tool with the 100-inch Hooker telescope on Mount Wilson. He hunted for faint Cepheids in the Andromeda Nebula, which many still thought was a nearby gas cloud inside the Milky Way. When he found them and measured their periods, the math was brutal. Andromeda was not a local mist. It was far beyond the known edge of our galaxy. Early numbers put it at around 900,000 light-years away. Later work refined that to about 2.5 million light-years. Either way, it was an entirely separate galaxy. With that one leap, Hubble shattered the idea that the Milky Way was the whole universe. Those faint smudges scattered across the sky were not minor decorations inside our system. They were island universes of their own, separated by gulfs so vast that even light needs millions of years to cross them. The cosmic map ballooned outward by orders of magnitude. But the ladder did not stop there. Beyond the range of Cepheids, astronomers turned to even brighter and more violent standard candles. White dwarf stars in close binary systems can slowly steal matter from their companions. As their mass creeps upward, there is a critical point at about 1.4 times the mass of the Sun. At that mass, called the Chandrasekhar limit, the white dwarf can no longer support itself. It collapses and detonates in a Type 1a supernova. These explosions are astonishingly bright, sometimes outshining an entire galaxy for a short time. More importantly for our ladder, they all reach nearly the same peak luminosity because they all explode at nearly the same critical mass. That makes them excellent standard candles, visible across billions of light-years. By measuring how bright a Type 1a supernova appears in a distant galaxy and comparing it to its known true brightness, astronomers can pin down the distance to that galaxy with impressive accuracy. This method became the top rungs of the ladder. Parallax calibrates the Cepheids in nearby galaxies. Those Cepheids calibrate distances to more distant galaxies. Those galaxies then calibrate the true brightness of Type 1a supernovae. And those supernovae finally reach out to the deep universe. Each rung stacks on the previous one. A 10% error down low becomes a 10% error all the way up, so every step has to be measured and remeasured with painful care. In the 1990s, teams using these supernovae expected to measure how much the expansion of the universe had slowed over time because of gravity. Instead, they found something far stranger. The expansion was not slowing, it was speeding up. That discovery of cosmic acceleration and the mystery of dark energy driving it will play a central role later in our story. For now, the key point is this. We did not simply imagine a huge universe. We built a ladder of methods that let us measure its size, from a finger held at arm's length, to tiny shifts of nearby stars, to pulsing giants in other galaxies, to the violent deaths of white dwarfs halfway across the cosmos. We turned the flat night sky into a three-dimensional structure. Only with that structure in hand can we start to ask meaningful questions about edges, because once you know that Andromeda is millions of light years away and that supernovae blaze billions of light years out, the word edge stops meaning what it did when people thought the stars were holes in a dome. By the early 20th century, the sky was getting crowded in a new way. Through larger and larger telescopes, astronomers kept seeing faint fuzzy patches, little whirlpools of light that did not look like ordinary stars. Some were clearly clouds of gas inside the Milky Way. Others, the spiral nebulae, showed delicate pinwheel shapes. The big argument was whether these spirals were small decorations orbiting inside our galaxy or enormous star systems in their own right, unimaginably far away. Depending on the answer, the universe was either huge or almost unspeakably huge. In 1920, that argument turned into what is now called the Great Debate. On one side stood Harlow Shapley, who had spent years mapping clusters of stars inside the Milky Way. He concluded that our galaxy was far larger than most people thought, maybe 300,000 light-years across, and that the Sun sat well away from the centre. To him, that enormous Milky Way easily had room to hold the spiral nebulae as little side structures. On the other side was Heber Curtis, who pointed to the brightness of novae that exploded inside spirals and to the dust lanes that made them look like flattened star disks. To Curtis, the spirals were separate island universes scattered through space far beyond the outskirts of our own. Both men had data. Both could tell a plausible story. Neither could deliver the knockout punch. You can argue all night about whether a light across a lake is a house on your shore or a distant ship unless someone rows out and measures the distance. In astronomy, that someone turned out to be Edwin Hubble with his Cepheid variable stars. By 1923, Hubble had time on the 100-inch telescope at Mount Wilson, then the most powerful eye on the skim, where he set out to find individual stars in the Andromeda spiral and see whether any of them blinked with the characteristic rhythm of Cepheids. When he found them and measured their periods, the numbers did not care about anyone's pride. Using Henrietta Leavitt's period luminosity law, those Cepheids placed Andromeda at a distance that completely dwarfed any plausible size for the Milky Way. Even the early rough figure of around 900,000 light-years already pushed Andromeda well outside our galaxy. Later refinements to the ladder moved that to about 2.5 million light-years. Either way, it was decisive. The fuzzy spiral was not a little weather pattern inside our system, it was another galaxy. Once Andromeda fell into place as an external galaxy, the other spirals followed like dominoes. Those scattered pinwheels across the sky were not side notes. They were peers of the Milky Way, each with hundreds of billions of stars. The universe was now a vast city of galaxies, not a single metropolis. This realization was as humbling as learning that Earth goes around the Sun, or that the Sun is not at the center of the Milky Way. We had been demoted again, this time from the center of everything to one suburb in a cosmic archipelago. With better photographic plates, bigger mirrors, and deeper surveys, astronomers started to count. In the region we can see, there appear to be on the order of 2 trillion galaxies. Each galaxy holds hundreds of billions of stars on average. Many of those stars almost certainly have planets. Even rough multiplication leads to numbers like 100 billion trillion possible worlds inside our view. That is a 1 followed by 23 zeros. It is gluttonous abundance. Yet the key phrase here is inside our view. We had accidentally smuggled a new concept into the word universe without naming it. To clean up the language, cosmologists draw a sharp line. The universe in the broad sense means everything that exists anywhere and any time. All of space, all of time, all matter and energy. The observable universe is a different thing. It is the part of the whole that we can in principle see from here and now, using any light or signal that has had time to reach us since the Big Bang. That restriction is not a matter of telescope power. It comes from 2 simple facts. Light has a finite speed, and the universe has a finite age. Light moves at about 300,000 kilometers per second, incredibly fast but not infinite. The universe has been around for about 13.8 billion years. Multiply those and you might expect the farthest distance we could see to be 13.8 billion light-years. but the real number is larger, about 46.5 billion light-years in radius. The reason is that while light has been travelling toward us, space itself has been stretching. The galaxy that sent us ancient light was much closer when it emitted that light. During the journey, expansion has carried it farther away so that by the time the light reveres, the source is well beyond 13.8 billion light-years. Put this together and the observable universe becomes a sphere centred on us with a present-day radius of roughly 46.5 billion light-years. Everything inside that bubble has had time, in principle, to send us light since the Big Bang. Everything outside it has not. That outer boundary is sometimes called the cosmic light horizon, but that phrase is a little dangerous because it tempts you into imagining a shell or a wall out there. It is not a wall. It is more like the horizon at sea. Imagine standing on a calm ocean with a clear sky. You can see ships, waves, and clouds out to a crisp circle where the water seems to meet the sky. Beyond that line you cannot see, but you know the ocean does not end there. If you sail forward, the horizon moves with you. There is no special ring of water at some fixed distance. There is only the limit of your view from wherever you happen to stand. The observable universe works the same way. From Earth, we sit at the centre of a visible sphere roughly 93 billion light-years across. That does not mean we live in a privileged location, and it does not mean there is a physical shell at that radius. An astronomer in a galaxy 40 billion light-years away would tell the same story, but with themselves at the centre. They would have their own observable universe, their own light horizon, their own sphere of radius 46.5 billion light-years. Part of their sphere would overlap with ours. There would be galaxies both of us can see and study, but they would also see regions we will never glimpse, and we see regions they never will. Every observer anywhere in space is always at the centre of their own observable bubble, simply because light has to travel outward from them and inward toward them. This is the moment where the idea of an edge starts to mutate. The observable universe has a clear outer limit defined by physics. Beyond that limit, light has not had time to reach us, and because expansion is accelerating, much of what is outside now will never be visible to us at all, no matter how long we wait. That is a real boundary on knowledge, enforced by the geometry of space and time. Yet it is not a border in the way the old cosmic domes were. You cannot fly your ship there and bump into it. You cannot paint a line on it. It is a horizon that always recedes as you move. So when we ask where the universe ends, one honest partial answer is already in hand. Our observable universe ends at a distance where early light, stretched and cooled by expansion, can just barely reach us today. That edge is about 46.5 billion light-years away in every direction. But that is only the edge of our view, not necessarily the edge of everything. To figure out whether there is any meaningful end beyond that, we have to ask a new question. Is what we see here typical of the whole, or are we living in a special bubble? That question leads directly to the cosmological principle and the idea that the most important feature of the universe might be how unremarkable our patch really is. Stand outside on a clear night far from city lights and slowly turn in a full circle. At first, the sky looks messy. Constellations here, a bright planet there, the band of the Milky Way slicing across one direction and nothing but scattered stars in another. But if you could zoom your mind out far enough, averaging over all the messy detail, you would notice something surprising. On the largest scales, our observable universe is boring. And that boring sameness turns out to be one of the most powerful clues we have about what lies beyond our horizon. Astronomers have spent decades turning the sky into numbers. They divide it into millions of patches and count how many galaxies fall into each patch, how bright they are, what colours they have, how fast they are moving. Nearby space looks like a chaotic web. Galaxies clump into groups and clusters. Clusters join into long filaments. Between those filaments lie enormous voids, empty regions tens of millions of light-years across where almost nothing shines. It would be easy to look at that cosmic spiderweb and conclude the universe is wildly uneven. The trick is to choose the right scale. Imagine flying low over a forest. From a few meters up you see individual trees, clearings, rivers and rocky outcrops. Nothing looks uniform. Climb in a plane and rise to 10,000 meters. Now the same forest turns into a smooth dark carpet. The details have blurred away, and you see average properties rather than individual quirks. The universe works the same way. On scales of galaxies and clusters, it is patchy and wild. On scales of hundreds of millions of light-years, It smooths out into statistical sameness. This directional sameness has a name: isotropy. A universe is isotropic for an observer if, when they look in different directions and average over large enough volumes, they see the same kinds of structures in every direction. Count galaxies in a giant cone of space pointed north and you get roughly the same density you would get in an equivalent cone pointed south or toward any other compass point. There are fluctuations, but they are small compared to the overall average. Isotropy shows up not just in galaxy counts, but in the oldest light we can see. The cosmic microwave background is a faint glow bathing the entire sky, left over from when the universe was only about 380,000 years old. When satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe and Planck measured its temperature, they found something stunning. In every direction, the temperature is essentially the same, about 2.7 degrees above absolute zero. The differences are at the level of 1 part in 100,000. If you coloured a full sky map by temperature, it would look almost perfectly uniform with tiny speckles of warmer and cooler spots sprinkled over it. Those tiny speckles are enormously important. They are the seeds of future structure, the places where gravity will eventually gather matter into galaxies and clusters. But the almost perfect uniformity tells us that, on the largest scales visible to us, the early universe did not have preferred directions. No special hot pole and cold equator, no cosmic north and south, just nearly the same conditions everywhere. Directional sameness is only half the story. The other half is sameness from place to place, which cosmologists call homogeneity. A universe is homogeneous if, when you look at different locations and average over large volumes, the properties are the same. You can think of isotropy as sameness when you turn your head, and homogeneity as sameness when you move to a different town. We cannot literally teleport to another galaxy to check whether physics is the same there. But light brings us evidence. When we look at distant galaxies in different parts of the sky, we see the same kinds of stars, the same periodic table of elements, the same spectral lines shortened or stretched by the same rules. Einstein's equations for gravity seem to work in galaxy clusters billions of light years away, just as well as they do in our own solar system. Supernova explosions, black holes, and the growth of large-scale structure all follow the same patterns wherever we look. Put isotropy and homogeneity together, and you get what is called the cosmological principle. It is a simple, almost modest claim. On large enough scales, the universe looks the same in every direction and from every location. No special directions, no special places. There are local quirks and structures, of course, but these are small ripples on top of a statistically uniform sea. This principle is not just a philosophical taste, it is built into the mathematical models that describe cosmic expansion. When cosmologists solve Einstein's equations for a universe filled with matter and energy, they usually assume the cosmological principle from the start. That assumption drops the complexity of the problem from impossible to manageable. The remarkable part is that when we then go and look, the real universe agrees with this simplification to high precision. There is another quiet idea hiding inside the cosmological principle, one inherited from Copernicus. It is the refusal to put ourselves at the centre by assumption. Once we learned that Earth is not the centre of the solar system and that the Sun is not the centre of the galaxy, it would be strange to insist that our galaxy occupies a privileged place in the universe. The cosmological principle is essentially a cosmic version of that humility. What we see from here is not special. Our observable bubble, huge as it is just one typical patch among many. If that is true, then something important follows for the edge question. When we look as far as we can in every direction and see roughly the same large-scale pattern, we are not looking at a special bubble with some rare structure inside. We are looking at a fair sample of the whole. Beyond our horizon, the safest bet is not that there is a dramatic change or a literal wall. It is that there is more of the same. More galaxies, more clusters, more voids laid out in the same web like patterns, extending far beyond what any telescope can reach. Of course, this is an extrapolation. We cannot prove that the universe is homogeneous and isotropic on scales larger than we can observe. But given the evidence in every direction out to our horizon, and given our track record of getting burned whenever we declared ourselves special, cosmologists treat the cosmological principle as a working rule. It says the edge of the observable universe is a limit of vision, not a qualitative border in the fabric of space. There is a subtle twist here. You might think an isotropic universe could still have us at the centre of something, like being in the middle of an expanding bubble. From the centre, everything looks the same in all directions, but if the universe were centred on us in that literal way, observers elsewhere would see a different pattern. Their sky would not be isotropic. To preserve isotropy for all observers, you need homogeneity too. Only a universe that is pretty much the same everywhere can look directionally the same from anywhere. So the cosmological principle becomes a kind of quiet anti-edge statement. It whispers that there is no preferred place where the universe begins or ends, no thickened shell where structure changes dramatically, at least not on the largest scales. Whatever boundaries we eventually find will have to be stranger and more subtle than a simple border between something and nothing. The next step is to ask what shape a universe like this can have. If it is roughly the same everywhere and everywhen, can it still be finite? Can it bend back on itself? Or does isotropy and homogeneity force it to be infinite? To answer that, we have to let space itself curve and flex under the weight of matter, and that means bringing Einstein into the story. So far, we have treated the universe like a vast room, more or less the same everywhere, full of galaxies instead of furniture, and with no obvious centre. The cosmological principle tells us the room is not special in any direction and not special in any location. The next natural question is what shape that room has. Is space itself flat like an endless floor, curved back on itself like the surface of a planet, or warped in some stranger way? To answer that, we have to stop thinking of space as a rigid container and let it bend. That is where Einstein walks on stage. In Newton's world, space and time are a fixed background. Gravity is a force that reaches across that background, pulling objects toward each other. Einstein flipped that picture. In general relativity, mass and energy tell space-time how to curve, and curved space-time tells matter how to move. Gravity is no longer a mysterious invisible tug. It is the natural motion of objects following the straightest possible paths in a geometry that is itself distorted. Imagine placing a heavy bowling ball on a stretched rubber sheet. The sheet sags. Roll a marble nearby and it curves inward, not because an invisible hand is yanking it, but because it is following the sloping surface. That image is not perfect, but it captures the core idea. Mass and energy change the geometry around them. Planets orbit stars because they are moving through curved spacetime, not because they are tied to them by unseen strings. Now zoom out. Instead of asking how a single star or black hole warps the space nearby, ask what the combined mass and energy of the entire universe does to the geometry on the larger scales. Einstein's equations do not just describe local bumps and dents, they also allow whole universes as solutions. Fill space with matter and energy, assume the cosmological principle so that on large scales it looks the same everywhere, and you get a small family of possible cosmic shapes. There are three big options. If the average density of matter and energy is greater than some critical value, space has positive curvature like the surface of a sphere. This is called a closed universe. It is finite in total volume but has no edge. You can walk around Earth's surface forever without finding a boundary that says end of planet. You would just keep looping. In a closed cosmic geometry, you could in principle travel in one direction long enough and eventually arrive back where you started, having circled the universe. If the density is less than the critical value, space has negative curvature, like a saddle or a Pringles chip. This is an open universe. It stretches out to infinity, even though its geometry is different from flat space. Lines that start parallel slowly diverge. Triangles have internal angles that add up to less than 180 degrees, yet there is still no edge. You can travel forever without hitting a wall or wrapping around. If the density is exactly at the critical value, space is flat on large scales. Flat here means that Euclidean geometry holds. Parallel lines stay parallel. The angles of a big triangle add up to 180 degrees. A flat universe is also infinite in extent, at least in the simplest models. Once again, no edge, just more of the same in every direction. So the global question about edges has become a question about curvature and density. Is our universe closed and finite with no boundary, or open or flat and infinite with no boundary? The boundary has slipped through our fingers. Instead of an end of space, we have different possible ways for space to never end. The key is to measure which case our universe actually lives in. How do you measure the curvature of something as enormous as the universe? You do it the same way you might test whether Earth is round or flat without leaving your continent. You look at large triangles and see whether their angles add up to more or less than 180 degrees. In cosmology, the triangles are made of light and structure, and the protractor is the cosmic microwave background. Remember that faint afterglow from when the universe was only a few 100,000 years old? At that time, the cosmos was a hot, dense gas where sound waves rippled through the matter and radiation. Those waves left a preferred physical scale, a characteristic size of hot and cold patches in the plasma. When atoms formed and the fog cleared, that pattern froze into the microwave background as a mottled texture of slightly warmer and cooler spots. If we know the actual size of those primordial ripples at the time they formed, and we measure how big they look on the sky today, we can infer the curvature of space between us and that ancient surface. In a closed universe, where space bends like a sphere, light beams converge. The same physical patch would look larger on the sky, covering a bigger angle. In an open universe where space curves like a saddle, light beams diverge, and the patch would look smaller. In a flat universe, the observed angle would match the expected size in a straight geometry. Satellites have now measured this pattern with extraordinary precision. The Cosmic Background Explorer first detected the tiny fluctuations. The Wilkinson Microwave Anisotropy Probe mapped them in detail. The Planck satellite then produced an even sharper full sky map, turning the microwave sky into a high-resolution image of early universe ripples. When cosmologists analyze how the strength of those hot and cold spots varies with angular scale, they find that the characteristic feature appears at about the angle expected in a flat universe. The numbers are striking. Within our observable region, space is flat within a few parts in 100. Planck's results suggest that if there is any overall curvature, it is smaller than about 0.4% of the critical value. That is like surveying a patch of ground 10 kilometers wide and finding it flat to within a few centimeters. From that local perspective, Earth looks perfectly flat, even though we know that over much larger distances it curves into a sphere. The same caution applies here. These measurements tell us that the part of the universe we can see is extremely close to flat. The simplest interpretation is that the whole universe is flat and infinite. That fits nicely with the data and with many models of cosmic inflation, which we will visit soon. But a very large closed universe could masquerade as flat within our limited horizon. If the cosmic sphere is vast enough, our observable bubble would be too small a patch to reveal the overall bend. So we end up with a layered answer. On the scales we can observe, the universe is astonishingly smooth and flat. There is no sign of a cosmic edge where geometry breaks, no indication that we live in a small pocket of strange curvature. Whether the whole is truly infinite or only unimaginably large and finite remains open. In either case, the old picture of flying outward until you hit a wall has dissolved. A closed universe has no edge because it loops back. An open or flat universe has no edge because it never stops. Curved space has turned the edge question from a hunt for walls into a hunt for geometry, and geometry has pointed us toward a universe that is either endless or effectively so. To understand why it is expanding in the first place and how the relic light and ripples we measure came to be, we have to rewind the clock to the beginning of time and watch the early universe ignite. Take the expanding universe we see today and imagine running the film backwards. Galaxies stop racing away and drift closer. Clusters contract. The great cosmic web tightens. Keep rewinding and everything you see on the largest scales gets crammed into a smaller and smaller volume. Temperatures climb, densities soar. At some point, the whole observable universe is squeezed into something so hot and dense that the idea of galaxies or even atoms stops making sense. That is the core idea behind the Big Bang. Not an explosion in pre-existing space, but the rapid expansion of space itself from an early state that was once unimaginably compressed. This picture did not come from philosophy. It came from Hubble's discovery that distant galaxies are redshifted in proportion to their distance and from Einstein's equations, which naturally allow expanding solutions. If space is stretching today, then yesterday it was smaller. Push back far enough in time, and the math says the density and temperature become extreme. That is unsettling but also powerful because a universe that started out hot and dense must leave behind specific fingerprints that we can look for here and now. Those fingerprints is the mix of light elements. In the first few minutes of cosmic history, conditions were hot enough for the entire universe to behave like the core of a star. Hydrogen fused into helium and traces of lithium in a process called primordial nucleosynthesis. The details depend on how hot the universe were, how fast it expanded, and how much matter it contained. When astronomers measure the abundances of helium and other light elements in old gas clouds and ancient stars, they match the predictions astonishingly well. That is one pillar of the Big Bang story. Another predicted fingerprint is even more dramatic. If the universe was once hot and dense enough to be a glowing plasma, then that glow should still exist today, cooled and stretched by expansion. In the 1940s, physicists George Gamow, Ralph Alpher, and Robert Herman worked out that a relic radiation field should fill space, now chilled from searing heat down to just a few degrees above absolute zero. For years, the idea floated around as the theoretical curiosity, largely ignored by observers who had no instruments designed to look for it. 2 decades later, in 1964, Arno Penzias and Robert Wilson were using a sensitive microwave antenna for radio astronomy and satellite work. No matter where they pointed it, they heard a faint, persistent hiss. They checked for interference from cities. They checked the electronics. They even cleaned out pigeon droppings from the dish. The noise did not go away. Eventually, they learned that another team of physicists had been searching for exactly such a signal. The hiss was not a glitch, it was the sky itself. What Penzias and Wilson had stumbled onto was the cosmic microwave background, the cooled afterglow of the early universe. When the cosmos was a few 100,000 years old, it was filled with a hot, dense gas of protons, electrons, and photons. In that state, light could not travel far without scattering. The universe was like the interior of a star, opaque and glowing. As expansion continued, the gas cooled until electrons and nuclei could join to form neutral atoms. Suddenly, photons no longer bounced constantly off free electrons. The universe became transparent. The light released at that moment has been streaming through space ever since, its wavelengths stretched by expansion. What began as visible and infrared light has been stretched into microwaves. Today it bathes the cosmos in a nearly uniform glow with a temperature of about 2.7 degrees above absolute zero. Point a microwave detector anywhere in the sky and you see it. You are literally looking at the baby picture of the universe, a snapshot taken when it was only about 380,000 years old. At first, the cosmic microwave background seemed astonishingly smooth. The temperature was the same in all directions to better than 1 part in 10,000. That uniformity was a triumph for the Big Bang. It meant the early universe had reached almost perfect thermal equilibrium. But it was also a problem. If everything started so smooth, how did we ever get galaxies and clusters and cosmic structure? A completely uniform gas just stays uniform. Gravity needs tiny overdensities to work with. In 1992, the Cosmic Background Explorer satellite announced something barely visible yet cosmically important. After careful measurements, it found tiny variations in the microwave sky. Some patches were a few parts in 100,000 warmer or cooler than average. Later missions, especially the Wilkinson Microwave Anisotropy Probe and the Planck satellite, mapped these temperature ripples in exquisite detail. The sky that once looked featureless now revealed a delicate speckle pattern of hot and cold spots. Those spots are not random noise. Slightly hotter regions correspond to slightly denser patches in the early plasma, places where gravity had a head start in pulling matter together. Slightly cooler regions correspond to slightly underdense patches. Over billions of years, those gentle seeds grew into the web of galaxies and clusters we see today. When computer simulations feed in the pattern of early fluctuations measured by Planck, and then let gravity run forward, they produce a large-scale structure that closely matches the real universe. The cosmic microwave background carries even more information hidden in the pattern of its ripples. By analysing how strong those variations are at different angular scales on the sky, cosmologists can infer the contents and geometry of the universe. It is like listening to the tone and overtones of a bell to figure out its shape and material. In this case, the data tell us that only about 5% of the cosmic energy budget is ordinary matter. About 27% is dark matter, an invisible substance that reveals itself only through gravity. Roughly 68% is dark energy, the mysterious driver of accelerated expansion. The same analysis also nails down the age of the universe, about 13.8 billion years, and confirms that space within our horizon is flat to high precision. In other words, the baby picture of the cosmos not only proves there was a hot, dense beginning, it encodes the recipe for what the universe is made of and how it is shaped. It is one of the most information-rich images humanity has ever created, yet the microwave background also exposes deep puzzles that simple Big Bang models cannot shrug off. One of them is the horizon problem. When we look at patches of the microwave sky separated by 90 billion light-years today, they have almost exactly the same temperature. But in a straightforward expanding universe without any special early phase, there is no way for those regions to have exchanged information or heat before the light we see was released. They were simply too far apart for light or any signal to travel between them. How did they end up so perfectly coordinated? Another is the flatness problem. Measurements show that the density of the universe is astonishingly close to the critical value that produces zero curvature. But in basic Big Bang models, any tiny deviation from that critical density would grow over time. A universe that started even slightly above the critical density would eventually recollapse. One that started slightly below would blow apart and become wildly open. For it to still be so flat today, the early density had to be tuned to an absurd precision, like balancing a pencil on its tip to 60 decimal places. These are not small technical issues. They hint that something important is missing from the simple picture of a universe that just expands smoothly from a hot, dense beginning. The cosmic microwave background is both a confirming shout and a whisper of deeper mysteries. It tells us the Big Bang really happened, it maps the seeds of structure and the contents of the cosmos, and at the same time it points toward an early chapter in cosmic history that the basic theory does not yet describe. The solution will turn out to involve an almost unimaginable growth spurt in the first fraction of a second, a period called inflation that changes how we think about size, edges, and what lies beyond our observable patch. The horizon problem and the flatness problem sound technical, but they are really both versions of the same unsettling thought. The early universe behaved too well. Regions that should never have had time to talk to each other somehow agreed on the same temperature. A density that should have drifted away from the perfect critical value somehow stayed balanced to ridiculous precision. It is like walking into a crowded stadium and finding every person wearing the exact same outfit in the exact same size. You can shrug and say coincidence, or you can suspect there is a deeper story. In 1980, physicist Alan Guth suggested that deeper story, and it was outrageous in exactly the right way. He proposed that in the first tiny fraction of a second after the Big Bang, the universe went through a phase of hyperexpansion called cosmic inflation. During this spell, space itself doubled in size over and over again at a rate that makes normal expansion look lazy. The whole thing may have lasted from about 10 to the minus 36 seconds after the beginning to about 10 to the minus 32 seconds. Those numbers are so small that even saying them feels wrong. But what happened in that blink reshaped everything. The basic idea is easier to picture than the numbers. Imagine a rubber balloon with little spots drawn close together. Before inflation, those spots are near enough that heat, light, and sound waves can slosh around and smooth things out. Everything inside the balloon patch shares the same temperature and density. Then someone blows the balloon up violently fast. The tiny patch that was once smaller than an atom stretches to a size far larger than the part of the universe we can see today. Points that were once snuggled together are now separated by billions of light years. Inflation is driven by a kind of energy locked into space itself. In many models, it is related to a field that sits in a high energy state, like a ball balanced at the top of a hill instead of resting in the valley below. While the field sits in this temporary state, its energy density stays nearly constant, and in general relativity, that kind of energy produces repulsive gravity. Instead of pulling things together, it pushes space apart. The result is exponential expansion. Every tiny bit of space creates more space, and the more space you have, the faster this runaway expansion goes. This violent growth spurt does two crucial things. First, it flattens the universe. Any initial curvature is stretched like the surface of a balloon, blown to enormous size. From the point of view of a small region inside, the surface now looks almost perfectly flat. That is exactly what we see when we measure the cosmic microwave background. Our observable patch is so large compared to the radius of curvature, if there is one, that the geometry inside it appears flat to high precision. Second, inflation solves the horizon problem. Before inflation kicks in, the region that will eventually become our observable universe is small enough that light and heat can move around and smooth out temperature differences. The early plasma comes into thermal equilibrium. Then inflation takes that already uniform region and stretches it to cosmic size. When we look at parts of the microwave sky that are now 90 billion light-years apart, we are looking at areas that once sat close together, sharing heat, before inflation ripped them apart. Their matching temperatures are not a coincidence. They come from a time when those regions really did talk to each other. Inflation does not just smooth things. Quantum mechanics, the theory that governs the smallest scales, ensures that the inflating field has tiny random fluctuations. Inflation takes those microscopic jitters and blows them up to astronomical size. Once inflation ends and normal expansion resumes, those stretched out quantum ripples become the slight overdensities and underdensities in the early universe. Over billions of years they grow into galaxies and clusters. This is not just a pretty story. Inflation makes concrete predictions about the statistical pattern of temperature fluctuations in the cosmic microwave background. The ripples should be almost, but not perfectly, the same strength on all scales, a property called nearly scale invariant. Their distribution should be very close to a Gaussian random field, which is a fancy way of saying the pattern of hot and cold spots should look like what you would get if you added up many small random contributions. Satellite measurements by the Wilkinson Microwave Anisotropy Probe and Planck show exactly that pattern. The match between inflationary predictions and observation is one of the big success stories of modern cosmology. There is a mind-bending side effect. If inflation happened, it probably did not happen in a neat one-shot way. In many models, inflation is generically eternal toward the future. At any given moment, there are regions where the inflating field has already decayed and inflation has ended, forming bubble-like universes that then expand more gently like ours. But in other regions, the field is still high, and inflation continues, stretching space faster than the bubbles can grow. Over time, you get a foam-like multiverse, an endless background of inflating space with bubble universes constantly budding off. Our observable universe would then be just one finite patch inside a vastly larger whole, probably one bubble among many. Whether or not that eternal inflation picture is literally true, the minimal message is clear. Inflation strongly suggests that the universe is much larger than the part we can ever see. Our cosmic horizon is not the edge of what inflation created. It is just our light speed limited window into that larger structure. That moves the edge question again. It is harder to imagine a neat border when your best theory for the early universe says that what you see is a tiny patch on an enormous quilt. Now jump forward by billions of years. After inflation ends, the universe coasts and then slows as gravity from matter pulls on everything. Galaxies form and structure grows. For decades, astronomers assumed this deceleration would continue. The open question was whether there was enough matter to eventually halt expansion and reverse it, or whether expansion would go on forever, slowing but never stopping. In the late 1990s, two teams took those Type 1a supernova standard candles and tried to measure how the expansion rate had changed over cosmic time. Distant supernovae show us the universe as it was billions of years ago. Nearby ones show us the recent past. By comparing their brightness and redshift, you can reconstruct how the expansion has evolved. Everyone expected to see signs of slowing. Instead, the data said the opposite. Distant supernovae were slightly dimmer than they should have been in a decelerating universe. That meant they were farther away than expected at a given redshift. The only consistent way to explain this was if expansion had sped up over the last several billion years. The universe, instead of coasting and slowing, had hit the gas pedal. The name we give to whatever is driving this acceleration is dark energy. It is called dark not because it is spooky, but because we do not know what it is. All we know is how it behaves. It does not clump into galaxies. It appears to be spread uniformly through space. Its energy density is roughly constant, at least so far as we can tell. In Einstein's equations, that kind of energy acts very much like the cosmological constant term he once added, and later regretted. It produces a gentle but relentless push that makes expansion accelerate. As the universe expands, matter gets diluted. Galaxies drift farther apart and their mutual gravity weakens. Dark energy, if it is truly a constant energy density of space itself, does not dilute. Every new cubic meter of space that appears carries its own dose of dark energy. Over time, this stuff dominates the energy budget. That is where we are now. Dark energy makes up about 2/3 of the total cosmic energy. It is the main driver of the universe's future. Inflation and dark energy are cousins in some ways. Both involve energy associated with space itself. Both enter Einstein's equations in similar mathematical forms. Both drive accelerated expansion. Inflation dominates for a brief instant at the beginning, then decays away. Dark energy takes over billions of years later and seems content to linger. Together they shape both the enormous size of the universe and its long-term fate. Once again, the concept of a simple edge slips further away. Inflation likely pushed the size of the universe far beyond what we can ever see. Dark energy ensures that distant regions will slip permanently out of causal contact as expansion accelerates. More and more galaxies will cross our event horizon and vanish from our future light cone forever. What we call the observable universe will shrink in content even as the whole keeps growing. In the distant future, an observer inside our merged local galaxy may see only a handful of stars and conclude that the universe is small and static. The real story will be hiding just beyond their reach. So far we have chased edges in space. We have asked whether the universe has a wall, a curve, or an infinite stretch of nothing but more of itself. Now turn the question sideways. Instead of asking where space ends, ask when meaningful change ends. What happens if we let the cosmic film play forward not for millions of years or even billions, but for spans so long that our language almost breaks? Does the universe have an edge in time? The starting point is what we already know. The expansion of space is accelerating and dark energy dominates the energy budget of the cosmos. As expansion speeds up, there is a tug of war between gravity on small scales and dark energy on the larger scales. Gravity keeps galaxies bound into groups and clusters. Dark energy pushes unbound regions apart faster and faster. Over tens of billions of years, that balance decides which structures stay together and which drift beyond each other's horizons forever. Our own fate at the scale of galaxies looks fairly clear. The Milky Way and Andromeda are on a slow collision course. In about 4 or 5 billion years, they will merge into a single large galaxy, sometimes nicknamed Milkdromeda in the literature, surrounded by a few dozen smaller companions in what is now called the local group. Gravity within this neighbourhood is strong enough to win against dark energy, so these galaxies end up in one bound island of stars. Everything beyond the local region gradually recedes so quickly that its light will never reach us again. Star formation does not go on forever. Stars are just engines that turn cold gas into light and heavier elements. Every new generation of stars uses up some of the available gas. Feedback from exploding stars and active black holes can blow gas out of galaxies altogether. Over hundreds of billions of years, the raw fuel gets used or locked away in compact remnants. New stars form more slowly and eventually stop. The last stars to shine will be small red dwarfs, the dim but incredibly long-lived runts of stellar families. While a massive blue star burns itself out in a few million years, a tiny red dwarf can sip its fuel for trillions of years. Long after our sun has died, these faint embers will still glow. Eventually, even they will fade. The universe will slowly transition into a phase where no new stars ignite. The visible cosmos becomes a collection of cooling stellar relics. In that far future, the main players are stellar corpses and dark objects. White dwarfs, the hot dense cores of dead stars, slowly radiate away their stored heat and become cold black dwarfs. Neutron stars and stellar mass black holes remain as compact fossils of earlier stellar generations. Planets, asteroids, and comets either get swallowed, smashed, or ejected into interstellar space. Over extremely long times, gravitational nudges between objects in a galaxy can fling stars out entirely, leaving behind a sparse population bound tightly to central black holes. Then even the black holes begin to lose their grip on eternity. According to Stephen Hawking, quantum effects near the event horizon cause black holes to emit a faint radiation and slowly lose mass. For a stellar mass black hole, the evaporation time is roughly 10 raised to the power of 67 years. For the supermassive black hole at the centre of our galaxy, it is closer to 10 raised to the power of 100 years. Those times are so far beyond human experience that they might as well be another kind of infinity. But they are still finite. Given enough time, even the largest black holes evaporate completely. After that, what remains is a universe in its heat-death era. Space keeps expanding, but almost all structured objects are gone. The The cosmos is filled with an extremely thin soup of low-energy photons, neutrinos, and perhaps a few light particles wandering across an ever larger volume. The temperature creeps closer and closer to absolute zero. Entropy, the measure of disorder or the number of ways the universe can arrange itself, has climbed to its maximum. There are no free energy gradients left to power processes, no chemistry, no stars, no machines, no observers. This is a different kind of edge. It is not that the universe falls off a cliff or ceases to exist. It is that nothing interesting can happen anymore. Time in physics is deeply tied to change. When nothing changes because everything is in equilibrium, the distinction between one moment and the next loses meaning. The heat-death scenario is a universe that continues forever in a boring, featureless state. In that sense, it is an end of time as a story, even if the underlying space-time persists. Heat-death is the default prediction if dark energy is truly a cosmological constant, an unchanging property of empty space. But that assumption might not hold. If dark energy is instead a dynamic field whose strength slowly changes, the future can look very different. One extreme possibility is that its repulsive effect grows stronger over time. In that case, the acceleration of expansion would not just continue, it would ramp up toward a catastrophic finale known as the Big Rip. In a Big Rip universe, the scale at which dark energy overwhelms other forces creeps downward as time passes. First it tears apart galaxy clusters, unbinding galaxies from each other. Later it overcomes the gravity that holds individual galaxies together and rips them into streams of stars. Still later, it exceeds the binding energy of star systems, flinging planets away from their suns. Near the end, the expansion pace outruns even molecular and atomic forces. Planets, rocks, and eventually atoms themselves are pulled apart as space stretches faster than any force can respond. All of this happens in a finite time. From the point where the late-time acceleration begins to the final shredding could be tens of billions of years, depending on how dark energy behaves. Current data lean against a dramatic Big Rip, but they cannot rule it out completely. The opposite extreme is a universe where dark energy weakens or reverses sign in the far future. If its repulsive effect fades and gravity from matter and any other components regains the upper hand, expansion could slow, stop, and then reverse. The cosmos would enter a contracting phase sometimes called the Big Crunch. Galaxies that once drifted apart would begin moving back toward each other. The cosmic microwave background, currently stretched into long microwave wavelengths, would be squeezed to shorter wavelengths and heat back up. As contraction accelerates, structures would collide and merge on ever larger scales. Temperatures and densities would soar. In simple versions of this picture, the universe would end in a state that mirrors the early Big Bang: hot, dense, and hostile to stable structures. Some speculative models go further and imagine that a crunch could bounce, turning one contracting universe into the seed of a new expanding one. In those cyclic or bounce ideas, the end of one cosmic history is the beginning of another, possibly in an endless chain of eons. Other approaches to quantum gravity also flirt with this kind of temporal recycling. In loop quantum cosmology, for instance, the equations describing space at extremely high densities can soften the singularity of a classical Big Bang into a bounce through a minimum size. Our expanding universe might then have inherited conditions from a prior contracting phase. Whether that prior phase had its own stars and galaxies or was something more abstract is an open question. The important point for our story is that in bounce and cyclic models, the edge in time is not absolute. It is a turning point where one phase gives birth to another. Right now, the best observational evidence favours a universe that will keep expanding forever at an accelerating or nearly accelerating rate. That makes heat-death the front-runner. But the data are not yet precise enough to completely rule out more exotic futures. We do not know for certain whether dark energy is truly constant, whether quantum gravity allows bounces, or whether some new physics will rewrite the script. What we can say is that in every scenario, the universe has some kind of temporal boundary, a heat-death limit where nothing more can happen, a ripping apart of all structure, or a crunch and bounce into something new. In that sense, time itself has an edge, not a moment you can visit with a spaceship, but a boundary in the story that the universe can tell about itself. Beyond that edge, there may be no observers, no complexity, perhaps no meaningful difference between before and after. When we ask where the universe ends, we cannot ignore this dimension. Space may or may not go on forever. but every plausible future holds a horizon in time, somewhere out there, where the breathtaking drama of stars, galaxies, and thinking beings comes to a close. When people say the universe might be infinite, it is tempting to translate that in your head as very, very big and move on. But infinity is not just a big number. It plays by its own rules, and those rules are deeply weird. To see what an actually infinite universe would mean, we have to step away from telescopes for a moment and spend some time with pure mathematics, where infinity has been poked and prodded hard enough to reveal its tricks. Only then can we bring those tricks back to cosmology and see what they imply about edges, copies, and how unique you really are. Start with something simple. Take the set of all positive whole numbers, 1, 2, 3, and so on forever. That set is infinite. Now look at the set of all even numbers, 2, 4, 6, 8, continuing without end. At first glance, the first set seems larger. It contains every even number plus every odd number. Yet you can match them up perfectly. Match 1 with 2, 2 with 4, 3 with 6, 4 with 8. Every whole number gets a partner, and every even number gets used exactly once. In that sense, the two infinite sets are the same size. This feels wrong because in the finite world, a part is always smaller than the whole. If you take half the marbles out of a box, you have fewer marbles than you started with. Infinity breaks that rule. An infinite set can be put into a one-to-one correspondence with a proper subset of itself. That is one of its defining features. It means that our normal intuitions about counting and comparing quantities are not safe once infinity enters the room. A famous thought experiment makes this even more vivid. Imagine a hotel with infinitely many numbered rooms and exactly one guest in each room. The hotel is full in the strongest possible sense. Every room is taken. Now a new guest arrives asking for a room. In an ordinary hotel, you would turn them away. In the infinite hotel, you simply ask every guest to move from room number n to room number n+1. The guest in room 1 moves to room 2, the guest in room 2 moves to room 3, and so on. Suddenly, room 1 is free, even though the hotel started out completely full. Now push it further. Suppose a bus arrives with infinitely many new guests. You can still fit them. Tell everyone already in the hotel to move to the room with double their current number. 1 goes to 2, 2 goes to 4, 3 goes to 6. All the odd-numbered rooms are now vacant, and there are infinitely many of those for the new guests. You have added infinity to infinity, and somehow ended up with the same infinity you started with. It is ridiculous and completely consistent at the same time. Mathematicians like Georg Cantor went even deeper and showed that there are different sizes of infinity. The infinity of whole numbers is one thing. The infinity of real numbers, which includes all decimals and irrational values, is strictly larger. You could spend eternity trying to match each real number to a unique whole number, and you would never succeed. There would always be leftovers. Some infinities are bigger than others. Infinity is not a single monolithic concept. It is a whole spectrum of strange. This matters for cosmology because once you start talking about infinite space filled with stuff, you are not just flirting with these ideas, you are committed to them. Imagine that space is infinite, roughly uniform on large scales, and either continuous or divided into tiny discrete chunks at something like the Planck scale. In either case, consider a region the size of our observable universe, a sphere about 93 billion light-years across. That region contains a finite amount of matter and energy. Now imagine listing every possible way you could arrange that matter and energy inside such a region. Every possible pattern of particles, every possible configuration of fields, every possible history that region could have. The number of possibilities is beyond enormous. Something like 10 raised to the power of 10 raised to the power of 120 in some estimates. A 1 with 10 to the power of 120 zeros after it. That is a number so vast that you cannot visualize it in any normal sense. But crucially, it is still finite. If the universe is infinite in extent and roughly uniform, there are infinitely many disjoint regions the size of our observable universe scattered through space. Think of an endless three-dimensional grid of huge spheres, each one a potential cosmic neighborhood like ours. Each region must be in one of those finite set of possible configurations. When you have infinitely many slots and only finitely many patterns to fill them with, repetition is guaranteed. There will be regions out there that are exact duplicates of our observable universe. Not just similar, but identical down to every last particle. In one of those regions there is an Earth. circling a sun sitting in a Milky Way, where a person with your exact genetics and history is watching a video or reading an article that is identical to this one, thinking the same thoughts at the same moment. Not just one such copy, but infinitely many. There are also infinitely many near misses, regions where everything is the same except you chose a different breakfast this morning, regions where one ancient quantum event went the other way and history veered off slightly, regions where dinosaurs never died, where the Milky Way collided with another galaxy long ago, where Earth never formed. None of this relies on exotic quantum many worlds or speculative multiverse landscapes. It is a straightforward consequence of combining a spatially infinite universe with simple probability. If you have infinite rolls of a finite but huge-sided die, every possible outcome occurs not just once but infinitely many times. In that picture, every possible arrangement of matter that does not break the laws of physics must exist somewhere. Every kind of star system, every pattern of galaxies, every long-shot history you can write down. There is a sharp limit here. We can never see or visit these duplicate regions. The expansion of space and the finite speed of light mean that parts of an infinite universe can be forever out of causal contact with us. Their light will never reach our telescopes. No amount of technology can bridge that gap. From our perspective, these copies might as well be in separate universes, even though in the simplest models they are just very, very far away in the same space. You might reasonably ask whether it even makes sense to talk about things that exist in principle, but can never be seen. Are we still doing physics, or have we slid into pure philosophy? Cosmologists argue about that. Some say that if infinity is the best fit to the data within our observable patch, then taking its implications seriously is just honest reasoning, even if some consequences are untestable. Others worry that attaching reality to unreachable regions stretches the meaning of science too far. Either way, the logic forces us to rethink edges again. In an infinite universe, there is no outer boundary where existence fizzles out. Instead, you get an edge in a different sense. Somewhere between local and global, the idea of uniqueness breaks. You're not sitting in the only version of this story. You are one thread in an immense tapestry that, if you zoomed out far enough, would show the same motifs repeating over and over in different places. The universe does not end with a wall, it dissolves into endless repetition. Infinity also comes with a darker twist. Once you accept an actually infinite space and time, you open the door to a new class of paradoxes about probability and typicality. In an infinite universe, almost anything that is not strictly forbidden by physical law will happen somewhere, no matter how unlikely it is. That includes not only whole galaxies forming, but also extremely rare random fluctuations that can assemble complex structures briefly out of chaos. In that picture, there is a sense in which the universe has so much room to play that the strangest possibilities can start to outnumber the ordinary stories we like to tell about ourselves. And that will force us, in the next step of our journey, to ask a disturbing question. If an infinite universe can randomly assemble conscious brains with fake memories, how do you know you are not one of them? If an infinite universe repeats everything that can happen, you are not just surrounded by endless copies of galaxies and planets and familiar histories. You're also living in a reality where the extremely weird becomes inevitable. Infinity does not only guarantee reruns of normal life, it also makes room for things that feel like nightmares written by a statistician. One of the strangest of these is the idea of the Boltzmann brain, a hypothetical observer that pops into existence as a random fluctuation out of chaos, complete with fake memories of a past that never happened. The name comes from Ludwig Boltzmann, a 19th century physicist who helped build statistical mechanics, the branch of physics that explains how large-scale properties like temperature and pressure emerge from the motion of countless particles. In his framework, the second law of thermodynamics, the rule that entropy tends to increase is not a magical command. It is a statement about probability. Most arrangements of particles are disordered. Very few are highly ordered. So a system will almost always drift from order toward disorder simply because disorder is overwhelmingly more likely. Boltzmann noted that in a universe that lasts long enough, extremely rare fluctuations can go the other way. Sometimes, by sheer chance, particles will momentarily line up into a more ordered state. The probability is tiny, but given enough time and space it will happen. Now, imagine applying that logic not just to a box of gas, but to the entire cosmos. In an infinite or extremely long-lived universe in thermal equilibrium, you would eventually see spontaneous temporary islands of order bubbling up out of chaos. Some of those islands might be as simple as a small crystal forming. Others, much rarer, might be as complex as a working brain with a pattern of activity that corresponds to a conscious mind. A Boltzmann brain is that mind. A self-aware pattern that assembles briefly out of random fluctuations in a high-entropy universe has a moment of experience and then dissolves back into noise. The memories inside that mind would feel as real as yours do. Childhood, family, education, all there. Yet in this scenario, none of those events actually occurred. They are just part of the random configuration that happened to arise. It is a horror story dressed in equations. The paradox comes when you ask what kinds of observers are more probable in such a universe. Building an entire low-entropy cosmos like ours from a random fluctuation is incredibly unlikely. Building a single brain with false memories is still incredibly unlikely, but far less so. It takes fewer particles arranged just so. In a universe that spends most of its existence in a near-featureless high-entropy state, most of the rare-ordered configurations should be the small ones. A single brain instead of a full galaxy. A momentary hallucination instead of a consistent history. Run that logic and you land in a deeply unsettling place. If the universe is infinite in space or time and dominated by equilibrium, then the vast majority of conscious experiences should belong to Boltzmann brains, not to evolved beings embedded in a long coherent history. Statistically, it would be more likely that you are one of those freak fluctuations than a product of 14 billion years of cosmic evolution. Your memories would then be fake, your apparent evidence about the past would be an illusion, and any reasoning based on them would collapse. Most physicists recoil from this conclusion, not just because it is disturbing, but because it undermines the basic ground rules of doing science. If your own observations and memories are overwhelmingly likely to be false, then you cannot use them to test theories or build models. Any framework that predicts that typical observers are Boltzmann brains is self-defeating. It saws off the branch it is sitting on. So cosmologists use the Boltzmann brain paradox as a sanity check. A viable description of the universe should make it far more probable that we are ordinary evolved observers than random fluctuations. That requirement turns out to be tricky to satisfy in some infinite scenarios. It touches on a broader issue called the measure problem. In a finite universe, talking about probability is straightforward. You count how many times something happens, divide by the total number of trials, and you get a frequency that stabilizes as the number of trials grows. In an infinite universe, that recipe breaks. If something happens infinitely many times and something else also happens infinitely many times, the ratio of those infinities is undefined. Infinity divided by infinity does not give you a well-behaved fraction. To make predictions in cosmology, you need some way to compare different infinite sets of events. You need a measure, a weighting scheme that tells you how to count observers and experiences. Different choices lead to different answers. You might decide to count observers inside regions of a certain size, or within a certain time slice, or weighted by how much volume they occupy. In eternal inflation models, you could cut off your counting at different times or at different scales, and then let the cutoff go to infinity. Each of these schemes handles the infinity in a different way, and they can disagree about what a typical observer should expect to see. This is not a minor technical quibble. The measure problem reaches into questions as basic as why the cosmological constant has the value it does, and whether we ought to see a universe with our particular mix of dark energy, dark matter, and ordinary matter. Some approaches to the multiverse landscape suggest that there are many possible universes with different physical parameters. To make sense of that, you have to ask what fraction of observers live in universes like ours, and those fractions depend on how you choose to count. Boltzmann brains sharpen the issue because they are so extreme. In many naive measures applied to infinite space or eternal inflation, the total number of late-time random fluctuations is infinite, and overwhelms the finite number of ordinary observers that arise in more orderly eras. To avoid being flooded by Boltzmann brains, you either need a measure that suppresses their weight, or a cosmology where conditions that allow them simply do not last long enough. For example, if dark energy decays in a finite time and the universe avoids an eternal heat death, there may not be time for Boltzmann brains to dominate. You might hope that quantum mechanics could rescue us, but it also brings its own brand of infinity. In the many worlds interpretation, every quantum event with multiple possible outcomes actually realizes all of them, each in a different branch of the universal wave function. When a radioactive atom has a chance to decay or not decay, the world splits into two branches, one where it decayed and one where it did not. Every measurement, every microscopic choice fans reality into a branching tree of possibilities. Over cosmic time, the number of branches becomes unimaginably large, perhaps infinite. Each branch contains a complete universe with its own history. Some branches look very similar to ours, others diverge wildly. If you combine this quantum branching with an already large or infinite underlying space, the total structure of reality becomes a vast, layered multiverse. There is the spatial repetition of regions we talked about before, and on top of that, the quantum duplication of histories. Probability in such a setting becomes even more subtle. When you ask what the odds are that you will see a given outcome of an experiment, you are really asking how the different branches are weighted. In standard quantum mechanics, those weights come from the squared amplitudes in the wave function, and they obey precise rules. But when you try to merge that quantum measure with cosmological measures over infinite space and time, you run straight into the same conceptual walls. The honest answer today is that we do not have a fully satisfactory theory of probability in an infinite or eternally branching universe. We have working rules that match experiments in the lab and observations in our sky, but when extended all the way out to infinity, those rules start to strain. Boltzmann brains and the measure problem are signals from the edge of our understanding, warning that our usual tools may not be enough when the sample size is literally unbounded. For our purposes, they add a strange new kind of edge to the universe story. Not a boundary in space and not just a limit in time, but an edge in reason itself. Somewhere beyond a certain scale, our ordinary ways of assigning likelihoods and making sense of typical experience begin to wobble. We can write down models where everything that can happen does happen infinitely many times, and yet we do not yet know how to say, in a fully rigorous way, what that implies about what you should expect to see when you look around. Once you start wrestling with infinity, quantum branching, and strange measures, one idea keeps sneaking back in from the edges. Maybe what we call the universe is not the whole story. Maybe it is just one piece of a bigger structure. The word for that bigger structure is multiverse, and it sounds like marketing for a superhero movie. Underneath the buzzword, though, are several serious proposals that almost fall out of our best theories, whether we like it or not. Each one offers a different way for reality to extend beyond our observable bubble, and a different sense in which there might be edges between universes. The mildest version is sometimes called the quilted multiverse. Start with a single universe that follows the cosmological principle and is spatially infinite or at least unimaginably large. Now divide that space in your imagination into non-overlapping regions about the size of our observable universe. Each region is its own cosmic patch with its own galaxies and history. Quantum randomness and chaotic dynamics ensure that the exact details in each patch differ. But as we saw earlier, there are only finitely many possible configurations for a region like ours. In an infinite quilt, patches must repeat. In that picture, the multiverse is just our universe extended. There is no separate outside realm, no different laws of physics, no special new dimensions. The edges between patches are completely artificial, like lines you draw on a map of the ocean. Still, from the point of view of an observer inside one patch, everything beyond the cosmic horizon might as well be another universe. You can never cross into those other squares of the quilt. Their light will never reach you. The edge here is defined by causality, not by a physical wall. Inflation adds a more dramatic twist. In simple versions, inflation is a one-time event. The whole universe inflates, inflation ends everywhere, and you get a single post-inflationary cosmos like ours. In more realistic models, the inflating field behaves like a quantum object. It does not decay uniformly. Instead, in some regions it slips down to a lower energy state and inflation ends there, forming a bubble of normal space that then expands more gently. In other regions, the field stays high and inflation continues, stretching those parts of space even faster. The result is eternal inflation, a never-ending process where new bubble universes constantly appear in a background that keeps inflating. Each bubble has its own Big Bang moment when inflation ends locally and ordinary expansion begins. Inside, physics looks familiar. Outside, the inflating background pushes other bubbles away faster than light can cross the gap. From within any one bubble, including ours, the others are forever unreachable, screened off by a kind of super horizon that no signal can cross. In this scenario, the edge of our universe becomes the bubble wall where our region of broken inflation meets the still inflating sea. that wall is not a place we can ever reach, because by the time light could get there, inflation in the surrounding space has already carried it absurdly far away. In practice, the bubble interior is all we can experience. Yet in the larger multiverse, our bubble is just one expanding sphere among many, embedded in an inflating space that never fully switches off. String theory, which tries to unify all particles and forces into vibrations of tiny strings, pulls in an even more baroque multiverse. It requires extra spatial dimensions that are curled up into intricate shapes at every point in space. Different ways of curling those dimensions produce different low-energy physics. Change the shape a little, and you change particle masses, interaction strengths, even the value of the cosmological constant. Calculations suggest a mind-bending number of possible configurations, often quoted as something like 10 raised to the power of 500. If eternal inflation is real, different bubbles could fall into different string vacua. One bubble might have a cosmological constant much larger than ours, so galaxies never form. Another might have a slightly different fine structure constant so that the chemistry does not work. A tiny fraction of bubbles might end up with parameters that allow complex structures and life. We find ourselves in one of those not because we are special, but because only those kinds of bubbles can contain observers at all. In this landscape picture, each bubble universe has its own effective laws of physics. The boundaries between them are literal in the sense that crossing from one to another would mean crossing domains with different vacuum states and different physical constants. Then there is the quantum many worlds, which does not care about inflation or extra dimensions. Remember that in this interpretation, every quantum measurement causes the universe to branch into different outcomes. These branches are all part of a single wave function that evolves smoothly according to the Schrödinger equation. They do not communicate once they separate. To you, reality seems to pick a single outcome. In the full description, both outcomes occur on different branches, each with its own copy of you observing its own result. This gives a kind of branch multiverse layered on top of whatever spatial or bubble structure exists. You can think of each branch as a separate timeline that shares a common past and then splits again and again with every quantum decision. A given bubble universe in eternal inflation is not a single history. It is a thick bundle of many quantum histories stacked on top of each other. You experience one strand. Many worlds says all the strands are real. Compared to inflationary and landscape multiverses, quantum many worlds does not give you new spatial realms with different constants. It gives you parallel versions of events that differ in the outcomes of quantum processes inside the same basic physics. In terms of edges, these branches are separated not by distance in space, but by distance in an abstract space of quantum states. There is no travel from one to another. The edge between branches is absolute in practice, enforced by decoherence, the process that keeps quantum superpositions from interfering once they have entangled with their environments. All of these multiverse ideas have a common feature. They are difficult or impossible to test directly. We cannot see other bubble universes, we cannot access other string vacua, we cannot exchange messages with other quantum branches. Critics argue that this makes multiverses metaphysical rather than physical. Supporters counter that if a multiverse emerges naturally from theories that are otherwise testable and successful, ignoring its existence just because parts of it are out of view is not intellectually honest. The debate gets sharpest around questions of fine-tuning. Our universe seems delicately balanced. Change the strength of gravity or the cosmological constant by small amounts, and complex life becomes impossible. One way to explain that is to look for a single deep theory that forces those values to be what they are. Another is to say there are many universes with different parameters, and we unsurprisingly find ourselves in one of the rare life-friendly ones. That second answer uses the multiverse and the anthropic principle together as an explanation. Whether you find that satisfying may depend on your temperament as much as your physics. At this point, edges have become more conceptual than physical. There might be bubble walls beyond our horizon, but we can never reach them. There might be other string vacua in other regions of an inflating landscape, but they are forever outside our light cone. There might be parallel quantum branches in which you made different choices, but they are separated from you by decoherence, not by kilometers. The universe may not end with a solid boundary. It may instead dissolve into layers of reality that are not directly accessible. And yet, even without direct access, these ideas shape how we think about our place in the cosmos. If there are countless other universes with different laws, our own feels less like the unique stage of existence and more like one theatre in a vast city of possible realities. If quantum branching is real, your life is one thread among many. If eternal inflation happened, our visible universe is a tiny bubble in a much greater foam. None of that changes the physics you experience day to day, but it changes the story you tell yourself about the edges of what is real. Up to now, our edges have been about where we can go and what we can see. Horizons in space, endings in time, limits set by light and expansion. There is another kind of edge that is more unsettling, not a boundary in distance, but a boundary in the reliability of the laws themselves. The rules of physics feel rock solid. They have carried us from the first fractions of a second after the Big Bang to the present with eerie consistency. Yet buried in our best theories is the possibility that those rules are only locally stable, that what we call empty space might be sitting on a trapdoor. In quantum field theory, empty space is anything but empty. It is a kind of medium filled with fields that exist everywhere. The particles we see are excitations of those fields. Each field has a lowest energy configuration called the true vacuum. That is the state where the field wants to rest if it can. But there can also be false vacua, metastable states where the field is stuck in a local minimum, like a ball resting in a shallow depression high on a hillside rather than at the deep valley below. It feels stable for a long time, but there is a lower energy state available. If our universe is living in a false vacuum, the laws of physics we know are tied to that temporary state. Particle masses, the strengths of forces, even the properties of dark energy can all depend on the value of fields like the Higgs field. A shift to a different vacuum would rewrite that script. The terrifying part is that quantum mechanics allows a field in a metastable state to tunnel into the lower energy state by a rare fluctuation. When that happens in one tiny region, a bubble of true vacuum forms. Once born, that bubble does not politely sit in place. The energy difference between the false and true vacua drives the bubble wall outward at nearly the speed of light. Inside the bubble, the fields settle into their new values. Outside, the old vacuum persists until the bubble arrives. There is no way to see such a bubble coming. Its boundary races forward as fast as any signal can travel. One moment you are living under one set of physical laws. The next moment, if any structures can exist inside the new vacuum at all, you are in a universe with completely different rules. What would it feel like? In most plausible scenarios, it would not feel like anything, because atoms and chemistry as we know them would simply fail to exist. If the Higgs field changed enough to give different masses to electrons and quarks, stable matter might be impossible. Forces could become too weak or too strong to allow complex structures. From our side of the bubble wall, there is no warning siren, no gradual lead-up. Vacuum decay is a clean break in the operating system of reality. The good news is that current calculations suggest our vacuum is at least incredibly long-lived. When physicists combine the measured mass of the Higgs boson and the top quark with the equations of the Standard Model, they find that our vacuum is either truly stable or metastable, with a lifetime hugely longer than the current age of the universe. You see numbers like 10 raised to the power of 100 years, which is a 1 with 100 zeros, as a rough scale. That is comfortingly absurd. Still, vacuum decay is not something we could ever completely rule out. It is a genuine possibility flowing from the same mathematics that successfully predicts particle physics experiments. It gives us a new kind of edge. Not an edge we can approach, but an edge that could in principle rush toward us with no warning, changing the rules as it passes. It is a reminder that even the most basic features of our universe may be contingent, depending on which vacuum it happens to inhabit. There is another speculative edge that people talk about, one that steps even further outside everyday thinking. It is the idea that the universe itself might be a simulation, a computation running on some deeper substrate in a higher level reality. In that case, the edge of our universe would not be a bubble wall in a quantum field. It would be wherever the simulation stops, in time, in space, or in resolution. The modern version of this idea is framed as a trilemma. Imagine that technological civilizations can, in principle, reach a point where they are able to run extremely detailed simulations of worlds containing conscious beings. Maybe they do this for science, or entertainment, or reasons we cannot guess. Then consider three broad possibilities. 1. Almost no civilization ever reaches that level. 2. Some do reach it but choose not to run many such simulations. 3. Many do reach it and run vast numbers of simulations. If the third option is true, then the number of simulated observers could vastly outnumber biological ones in base-level reality. In that case, the argument goes, a random observer drawn from the whole collection is much more likely to be simulated than base. Your experiences, in other words, would be more likely to belong to a mind in a computer than a mind in a planetary brain. The simulation hypothesis does not say this must be so. It says that if advanced civilizations both can and do create many detailed simulations, then most observers should expect to be simulated. It is a clever piece of reasoning which but it runs into a wall when we try to treat it as physics. What would count as evidence that we are in a simulation? Some people suggest looking for glitches in physical law, places where the rules of the game break down unexpectedly. Others imagine that the underlying computational grid might leave traces, such as preferred directions or maximum energy scales that show up in high-energy experiments. So far, every serious test of our best theories finds smooth, continuous behaviour. Where anomalies do appear, physicists first assume they point to new natural physics, not to cosmic software bugs. Even if we did find something odd, interpreting it as proof of a simulation would be almost impossible. Any pattern you identify as evidence could itself be part of the simulation. The simulators could choose to hide their tracks or to fake whatever evidence they like. Worse, the hypothesis invites an infinite regress. If we are simulated, the world that runs our simulation might itself be simulated by something else, and that world by another, and so on. Somewhere there would need to be a base level, but we would have no way to know where we sit in the stack. That makes the simulation hypothesis effectively unfalsifiable by any experiment we can imagine. You cannot send a probe to the end of the grid and knock on the glass. You cannot step outside the system to examine the hardware. In that sense, the simulation edge, if it exists, lies permanently beyond our reach. The idea can be an interesting philosophical toy. It can inspire science fiction. It can even be used as a thought experiment about probability and typical observers. But by the normal standards of science, it sits outside what we can test. Vacuum decay and simulations represent two very different visions of where the universe might end. In one, the laws of physics we rely on could one day be replaced in an expanding bubble of new vacuum, erasing everything we know. In the other, the universe might end not with a bang or a whimper, but with someone pulling the plug on a calculation. In both cases, the edge is not something we can fly toward. It is a limit on how far our understanding and our methods of inquiry can reach. These possibilities bring us to a final kind of boundary, one that does not live in space or time or code, but in knowledge itself. No matter how good our telescopes and theories become, there may be questions about the ultimate extent and origin of reality that are forever beyond what experiments can touch. In the next step of our journey, we will face that head-on and ask what it means to do science in a universe where some truths may be real, but permanently out of reach. By this point, the universe probably feels less like a place and more like a riddle that keeps redefining itself every time we think we are close to the answer. We started with a simple question about where it ends and uncovered expanding space, invisible energy, infinite copies, bubble universes, unstable vacuums, and simulations. It is natural to wonder whether we have wandered beyond science into pure imagination. Somewhere in all of this, we have to ask a quieter but crucial question. What can we actually know? Where is the edge of knowledge itself? Science has never promised that everything is knowable. What it promises is more modest and more powerful. Given a world that behaves in regular ways, you can build models, make predictions, test them, and keep the ones that work. That cycle only reaches as far as observation and experiment can go. It leans heavily on the idea that the past has really happened, that the instruments on your desk are not hallucinations, and that the universe is not maliciously tricking you. For most of physics, those assumptions are so natural we barely notice them. On the scale of the entire cosmos, they become a choice. Think about the observable universe. We know it has a horizon because light moves at a finite speed, and the universe has a finite age. No matter how good our telescopes get, we cannot see beyond the distance that light has had time to cross since the Big Bang. That is not a technical limitation. It is a structural one. There are galaxies out there whose light is still on the way, whose entire histories will play out forever beyond our view. We can still make educated guesses about those unseen regions, and we do. The cosmological principle says that on large scales, the universe is homogeneous and isotropic. When we look in every direction out to our horizon and see the same statistics for galaxies and and microwave background ripples, we tentatively extend that pattern beyond our view. We say that the part we can see is typical, that the rest is more of the same. We cannot check that directly. We adopt it because it is the simplest story that fits the data, and because every time we thought we were at the center of something, we were wrong. The multiverse ideas stretch this pattern further. Eternal inflation, the string landscape, quantum many worlds. Each arises as a natural extension of theories that do make testable predictions in our universe. Inflation explains the microwave background. String theory provides candidate particles and interactions. Quantum mechanics is verified every time a laser works, but the parts of those theories that talk about other bubbles or other branches may themselves be forever unobservable. We are left with a mix of solid experimental success and speculative extrapolation hanging off the same equations. This is where philosophy quietly joins the conversation. What counts as a scientific claim? One answer is that a claim must lead to specific predictions that could be proven wrong by some conceivable observation. Another is that it is enough if the larger framework that implies the claim is testable and successful, even if some consequences are out of reach. Under the first standard, some versions of the multiverse and the simulation hypothesis sit outside the science. Under the second, they become part of our best description of reality, whether we like them or not. Either way, there are questions that slide beyond our reach. Is the universe truly infinite or just incredibly large and finite? If there are other bubble universes, how many are there? Does the full landscape of possible physical laws actually get realized? Is there a base-level reality below any simulations? We can write down models and argue about which ones are simpler or more elegant. We can look for indirect hints in subtle patterns in the cosmic microwave background or in the distribution of galaxies. But we have to admit that some answers may never be pinned down by data. That does not mean we should stop asking. Pushing up against these limits sharpens our understanding of what counts as evidence, what counts as explanation, and where probability theory breaks down. The Boltzmann brain paradox is not just a creepy story about fake memories. It is a stress test for any cosmology that includes infinite time and space. The measure problem is not just a complaint about equations. It is a sign that our usual ways of counting and comparing might need to be rewritten for an infinite context. These are not failures. They are frontier markers. There is also an emotional edge here. Realizing that some aspects of reality might be forever hidden can feel disappointing, even unfair. We like the idea that the universe is a giant puzzle, and that with enough time, patience, and cleverness, we could in principle solve all of it. The real situation is stranger. There are puzzles we can solve and puzzles whose solutions exist but sit beyond any possible experiment. The universe might know the answer, in some abstract sense, while we never can. Yet even within those limits, the progress we have made is astonishing. A species that only recently learned to harness electricity has measured the age of the cosmos, mapped its geometry, weighed its contents, and traced its history back to the first fractions of a second. We have detected the afterglow of the Big Bang, watched galaxies from when the universe was less than 1 billion years old, and inferred the presence of dark matter and dark energy from their fingerprints on cosmic structure. We have taken the same equations that describe falling apples and used them to decode the motion of galaxies billions of light years away. Notice something else. As we push toward the edges of knowledge, our picture of the universe did not become simpler, it became more layered and more strange. A flat, infinite cosmos that repeats patterns, an early era of inflation that might spawn endless bubble universes, quantum branching quietly filling the space of possibilities with parallel histories, dark energy pulling everything apart, possible vacuum decay lurking in distant futures. We did not trade mystery for certainty. We traded simple mystery for structured mystery. What do we do with that? On a practical level, we keep doing what physics has always done. We build better instruments to probe the cosmic microwave background, the distribution of galaxies, the behavior of dark energy. We search for new particles that could be dark matter. We test general relativity and stronger and stranger regimes with gravitational waves and black hole images. Each new measurement could confirm our current big picture or force us to revise it. Either way, the boundary of what we can know moves outward. On a human level, acknowledging the limits matters just a moment more. It forces humility. The universe does not owe us complete transparency. We happen to exist in a tiny window of cosmic time. on one planet around one star inside one galaxy, in what might be one region of an unimaginably larger reality. We get whatever clues reach us through light, gravity, and particles. From those clues we reconstruct an enormous story. Some chapters are rock solid, some are sketches at the edge of the map, some are bright question marks, and that brings us back quietly to the original question. Where does the universe end? After all this wandering, we are ready to give an answer that is honest about both what we know and what we do not. To do that, we need one more step, a final turn that brings the edges of space, time, law, and knowledge together into a single view and asks what they mean for us. We began with a very human question. Where does all of this end? If the universe is a thing, then surely it must have an outside, a border, a last stop beyond which there is only nothing. That instinct comes from a life spent inside rooms, boxes, countries, bodies, all wrapped in boundaries. Every object you have ever touched has an edge. It would be strange if the universe did not. Yet step by step, the picture we have built tells us something deeply counterintuitive. The more we understand, the less the universe behaves like an object at all. On the larger scales, space is not a solid container but a flexible stage. It bends around mass and energy. It stretches as the universe expands. There is no central point where the Big Bang happened. The expansion is everywhere. The observable universe does have a boundary at 46.5 billion light-years in radius, but that is not a wall. It is a light travel limit. Beyond it, there is almost certainly more universe, just hidden from us because light has not had time to arrive. Move to another galaxy and the observable sphere shifts with you. Everyone is at the center of their own bubble of visibility. No one is at the center of everything. We do not yet know whether the entire universe is infinite or only very large and finite. Measurements of the cosmic microwave background and large-scale structure say that space is flat to high precision. The simplest way to read that is that space goes on forever. In that case, there is no outer edge, just galaxy after galaxy, cluster after cluster, web after web, stretching without end. A traveller with unlimited fuel and invincible engineering could fly in one direction forever and never find a place where space stops. The only edges they would meet are horizons set by light speed and cosmic expansion. If space is not truly infinite but wraps around in a closed geometry, the situation is just as strange. A closed universe can be finite in volume yet have no boundary. The way the surface of Earth has finite area but no edge you can fall off. Travel straight long enough on that globe and you eventually return to where you started. In the same way, a closed three-dimensional universe might let you fly straight and eventually loop back to your starting point from the other side without ever crossing a border. Once again, no wall, just geometry that refuses to give you an outside. Inflation pushes both cases into something bigger. In almost every realistic inflation model, the region that became our observable universe is a tiny patch of a much larger inflated whole. Even if the cosmos as a whole is finite, it is so much larger than what we can ever see that our horizon is like a peephole in a cathedral wall. In many models, inflation never ends entirely. It keeps running in distant regions, spawning bubble universes like ours in an ever-growing foam. From inside one bubble, the others are unreachable. From the view of the larger picture, our entire observable universe is just one droplet in a storm. Time adds its own boundaries. The universe had a hot, dense beginning. Whatever deeper story may sit underneath that, the expanding plasma we can trace back through observations clearly reaches a moment about 13.8 billion years ago, where the physics becomes so extreme that our current theories run out of road. On the other side of time, dark energy drives an expansion that will almost certainly keep going. Stars will burn out, black holes will evaporate, and the cosmos will drift toward a thin, cold state where almost nothing happens. Whether that heat death is truly the end of all dynamics or one phase in a larger cycle depends on physics we have not yet nailed down, but every plausible scenario comes with some kind of temporal horizon where the rich drama of galaxies and life fades. Then there are edges in the rules themselves. Our vacuum might be absolutely stable. It might also be a long-lived but temporary state perched above a deeper energy minimum. If so, quantum mechanics permits a vacuum decay, a phase transition that would rewrite the laws of physics inside an expanding bubble racing at light speed. That is not something we have evidence for. It is simply something our equations allow. The point is not to lose sleep over it. The point is that even the laws we treat as fundamental could be local, tied to which valley, in a larger landscape of possibilities the universe happened to roll into. Layered on top of all that is an edge in what we can measure and prove. We can watch the cosmic microwave background and map the distribution of galaxies. We can test general relativity with gravitational waves. We can constrain dark energy and search for dark matter. But if there are other bubbles with different constants, we cannot see them. If there are quantum branches where history went differently, they are beyond communication. If the universe is infinite and repeats patterns, the copies lie forever outside our horizon. If we are in a simulation, any evidence could be faked by the simulation itself. At a certain point, questions about ultimate reality change from empirical ones to philosophical ones. The universe has answers. We just may not have a way to hear them. So after all of this, what do we actually get to say? Where does the universe end? Here is the most honest answer. The part of the universe we can observe ends at our cosmological horizon. Beyond that, there is more universe, probably a lot more, but its details are hidden behind the finite speed of light and the history of expansion. Space itself most likely does not have a hard boundary. It either continues forever or wraps around in a way that has no edge. Time has a beginning we can describe and a future we can sketch, both of which act as temporal edges for structure and complexity. The laws we know may sit inside a larger space of possible laws. Our methods of science operate inside a still narrower circle of what can be observed and tested. In other words, the universe ends not with a line you can cross, but with a set of limits. The limit of how far light has travelled since the Big Bang. The limit of how far gravity can hold structures together against dark energy. The limit of how long stars and black holes can operate before entropy wins. The limit of which vacua are stable. The limit of what we can ever measure from our one little world line through space-time. When you push past those, you hit not a wall of brick or fire, but a horizon where your questions start to outgrow what observation can answer. That might sound bleak. It does not have to be. The fact that there are questions forever beyond us does not diminish what we have already done. On a small rocky planet around an ordinary star, a species of pattern-seeking primates figured out that the sky is not a dome, that the stars are suns, that there are billions of galaxies, that space is expanding, that there was a hot, dense beginning, that invisible matter and energy shape the cosmos, that the geometry of space is almost flat, that quantum fluctuations seeded every structure we see. We took the faintest signals from old light and rare particles and turned them into a coherent story of almost the entire visible universe. And here is the twist. In a universe that may be endless, indifferent, possibly infinite, your perspective is still uniquely yours. Out of all the possible arrangements of matter, you are one that can look up at the night sky and connect dots into meaning. You're made of atoms forged in stars that died billions of years ago, now arranged in a pattern capable of asking about the end of everything. That is not cosmic importance in the old sense. No destiny, no special center. It is something quieter and maybe deeper. You are part of the universe that has become aware of itself and curious about its own edges. So when you step outside after this and look at the sky, you are not just seeing distant lights, you are seeing back in time, out toward the horizon of what is observable, and sideways into the mystery of what is not. You're standing at the edge of your own knowledge, which is also the edge of what any mind on Earth has ever known. Beyond that lies a vast reality, some of which we will map, much of which we will only infer, and some of which will stay forever beyond us. The universe may not have the kind of edge you can touch, but it has the kind that matters for minds like ours. A frontier that moves outward every time we ask better questions, build better instruments, and challenge our assumptions. A horizon that never disappears, only shifts. If that journey feels worth continuing, then you already know what to do next. Keep following the questions wherever they lead. Keep learning, keep wondering, keep looking up. Because as long as we are here to ask where the universe ends, the story of the universe has not finished telling itself.